I'm Daniel Main, and I've been here for about a year and a half. And one of my projects is to use VSim to model corona discharge. And so in this talk, I'll go over some background on what that is and what makes VSim unique, and then we'll go over some results. So just a bit of background on what is corona discharge. It basically, whenever there's a potential difference between two boundaries, corona discharge will occur. So I think everyone's experienced being shocked when they go to open a door, particularly if it's very dry. These boundaries could be conductors or dielectrics. So in this example, one boundary is a conductor, the other boundary is a dielectric. Now in this process, when I first got started, it took me some time to realize that the electron actually already needs to be there in order for corona discharge to occur. This could come about through a stray cosmic ray, it could be from UV light, but there does need to be a source for that electron. And you may find this kind of odd, but in actuality, this happens pretty regularly. It's just that at normal atmospheric pressures, when there's no potential difference, we would never even notice that the electron had formed or had been emitted. But if a potential difference does exist, then the electron is accelerated, it bombards another neutral, creating more free electrons, and you get this cascade effect. So before I get into those details, first let me explain a little bit about what is VSim. VSim is the entire computational engine, visualization setup, post-processing, and data visualization package. The computational engine is called Vorpal. And so let me unpack some of these words. We say VSim is a multi-physics, fully kinetic electromagnetic particle and cell software. So multi-physics means we do plasma physics plus associated physics. So for example, reactions with neutrals, secondary emissions from boundaries, and other processes. Fully kinetic means that in principle, all plasma processes can be captured. So electrons and ions are treated kinetically. So we can look at non-Maxwellians. We can look at sheaths correctly. Now, this isn't always possible. This is often not possible in practice just because the timescales are too long. There's too many particles that are needed to resolve the physics, etc. But there are many, many problems where a kinetic approach can be used. And electromagnetic means that we're solving Maxwell's equations at each time step using the plasma current and charge density as source terms. And for a special case of that is what's often called electrostatics, which doesn't mean the problem is static. It just means that there's no self-consistent magnetic field. Okay, so why would we want to use VSim for modeling corona discharge? As I just stated, VSim computes the fully self-consistent electric field. So the way the problem is set up is the boundary conditions determine the initial acceleration. But once the plasma starts to form, the self-consistent electric field modifies this initial field appreciably, and we'll see that. But to capture this physics correctly, you have to allow the boundary conditions, you have to allow the potential to float at the boundary conditions. One way of doing that would be to use Neumann boundaries, which is what I've done. But VSim can capture all that physics. If you set this problem up as, if it's a 3 dimensions, there's going to be 6 boundaries. If you assign the potential at all the boundaries, you would not be doing the problem correctly simply because the boundary conditions would be determining the potential. VSim can compute the electric field and the dielectrics correctly, and this can be essential for modeling the breakdown of materials. Now, one thing to note is that things that, these processes occur on multiple timescales. So there's sort of the electron time scale, there's the ion time scale, and then there's the material breakdown time scale. So you wouldn't be able to do all that in one model, or at least it'd be very tough. VSim includes many collisional processes and secondary emission models. So the collisions with neutrals are through what's called the direct simulation Monte Carlo method. And the nice thing about this method is there's very few assumptions involved in modeling this. So we can do lots of different pressures without worrying about, how the equations, for example, in a fluid model would be set up. Now, a neat thing that's coming is that in VSim-11, we'll be able to import CAD drawings and assign dielectrics to each piece in the electrostatic field solve. And I'll talk about that more in a few minutes. So now let's get on to the setup of the problem. So this is a snapshot of the geometries. So down here, I've got a conductor, which I've set to 0 volts. And then up here, I've got a conductor, and embedded in this conductor is a dielectric. Now the scales here are on micrometers. So this is 200 micrometers, and then this is 300 micrometers. So let me get into a few basics to understanding this problem, or a few basics to understanding how to use the collision model that we have in VSim correctly. This is really important in order to get the problem right. And if you don't set it up right, the code will run just fine. I just wouldn't necessarily believe the output. So these aren't numerical constraints. These are constraints to get the physics right. So the easiest way to model collisions is with cross-section tables. So you'll need to go find your cross-section tables. If you have trouble finding those, I'm more than happy to help you find them. I use a few different sources. And then when you include collisions in VSim, you need to make sure that you're resolving the smallest mean free path. And the reason is because the collision model is a pairwise process within a cell. So in other words, you'll take a neutral and for an electron, for example, and the Monte Carlo method will be used to determine whether or not that collision occurs. And then depending on the type of collision, it will then compute the new trajectory, the new velocity. It could be an ionization collision. So if a collision occurs, a new electron would emerge, etc. But that determination of whether or not a collision occurs is a pairwise process. And physically, that a collision really can only occur if two particles are within the mean free path. And so therefore, the grid size needs to be smaller than the mean free path. Typically, elastic collisions have the largest cross-section and therefore the smallest mean free path. To speed up these calculations, VSim uses the no time counter method to reduce the computational time. And again, I want to emphasize that typically your grid size should be smaller than the smallest mean free path divided by 2. So, and then likewise, the time step should be smaller than an inverse collision frequency divided by 2. So these are just some constraints that you need to keep in mind when you're using collision model. So let me show you how I do that in VSim as a safeguard. What I do is, so let me just go through. This is the visualization window for one of my simulations. And so what I did was I input a gas pressure in torr. So these are at a 0.5 atmosphere. And then under the parameters, I went ahead and converted that to pascals. I computed a density using the ideal gas law. And then my mean free path is 1 over sigma divided by the gas density. Where sigma, what I do is I put in the largest cross section for the collisions that I want to include. So I've included that sigma up here as one of my constants. And then I just say dx. In this case, I set dx equal to the mean free path. This would be the largest you could make it. And the reason I did that was because half an atmosphere is pretty dense, and this was a pretty computationally intensive. So I just needed to reduce the number of grids. And so because it's 3D, if I made dx half, then I would have 8 times the number of particles and cells. And then likewise for the collision frequency, I also compute the collision frequency based on that sigma. And I actually have 2 time steps. I took the collision figured out the collision frequency, inverted that for the collision period. And dt1 is just the collision frequency over 3. But there's actually another constraint on the time step, and that is that as my electrons accelerate, as they get due to the potential difference, they pick up speed, and an electron can't cross a cell, can't cross more than 1 cell in a time step. So I also compute that time based on the potential difference. And then for my final one, I just take the minimum of that. Again, none of these are numerical instabilities, but rather you will just get incorrect results. Okay, so my boundary conditions are set that y min and y max. So this is the y-axis here. So I set the potential down here, and I set the potential up here, and then my other 4 boundaries are all Neumann boundary conditions, and that allows the potential to float. And you'll see why that's important when we start looking at the results. So furthermore, in VSim, we have lots of particle boundary conditions. In secondary emission boundary, we have lots of ways in which particles can interact with the boundary. We can have secondary emission. And one of those is that particles can accumulate on dielectrics. And this further influences the field. So let me go a little bit into the physics of this. And then I'll talk about the parameters for setting up the simulation, and then we'll look at some results. So Paschen's curve determines the necessary potential difference for a discharge to occur. But these are some important things about the derivation of Paschen's equation. One is, again, the existence of a pre-existing free electron. The creation of further free electrons is only achieved through impact ionization. Now, when the equations were derived for this, the one thing that was assumed was that this was the only collision. But really, that's not the case. Really, there's going to be lots of collision types, including there could be charge exchange, there could be excitation collisions. There could be collisions with, and I'll show you how to include collisions here in a little bit. But there could be elastic collisions. So in fact, there's definitely going to be elastic collisions, and that's going to affect the energy of the electron, which will affect the impact ionization collisions. So VSim can include all these collisional processes to get a more realistic corona discharge simulation. Each ionized atom leads to only 1 free electron, But in practice, multiple ionizations could also occur, and you could include these in VSim. And free electrons at the cathode surface are created by impact ions. So this was part of Paschen's original derivation. You can include secondary emission of electrons off of the cathode from ions. This would occur on much longer timescales than what I'm going to show you here. And I'll talk about that towards the end. So these are some of the Paschen's curves for different materials. So this is helium for neon, argon, hydrogen, and nitrogen. So this axis here is the potential difference. And then the horizontal axis is pressure times distance. And I found this paper where his original equation was derived. And I used that. I just wrote a little Python script to derive my own potential difference. So P in this equation is pressure in kilopascal, D is distance in meters, K is a constant which depends on PD, and that's given in the paper. And so for my setup, I determined that the voltage potential difference should be 923 volts. So these are some of the parameters from the simulation. I assume nitrogen, background gas, neutral pressure of 0.5 atmosphere. My cell size is 3 micrometers with a domain size that's about 500 micrometers. For these simulations, I only included ionization collisions. And the reason I did that was because if I included the other collisional processes, the mean free path was even smaller, and I'd have to make the grid size even smaller. So remember, you have to resolve the smallest mean free path to get the physics correct. And so including other types of collisions with larger cross sections meant smaller mean free paths. But certainly that's something that you could include in this simulation. So I ran this on 12 cores with on a machine that had 80 gig of memory, and that was already taxing it, and it would for a 3-dimensional simulation. So if you want to dig deep and do a lot of these sorts of collisions, you're probably going to need a minimum of, especially if you want to do it 1 atmosphere, 24 cores would be a good start. I included the dielectric with a relative permittivity of 9. Again, I fixed the upper and lower potentials, but the other 4 boundaries are Neumann. So this is just a few results towards the end of the simulation. What you see are secondary electrons. Those are the yellow population, and then the red dots are the nitrogen ions. And you can, of course, visualize all of this in VSim as a movie. So in VSim, once the simulation is complete, you just click on the Visualize tab and it pulls up all the data. One of the things that you will need to do, though, is actually use a post-processor called create missing particle dumps. And the reason you have to do that is because for example, the secondary electron population doesn't form. Let's say it forms within 10. Let's say it forms within 100 time steps. So you start the simulation. The free electron is accelerated. It hits a nitrogen atom. It ionizes an electron. That gives you a secondary electron. Let's say that happens at time step 100. Then the first saved data dump will be at time step 100. But I want to make sure all the data is synced. So to make sure all the data is being displayed at the same time step, then you just need to run this analyzer so that all of the data, when I'm looking at time step 0, I'm looking at only particles from time step 0. So if we wanted to look at nitrogen, plus and secondary electrons. Let me actually take a step back. So I'll just go ahead and do this from scratch. So the data overview tab in VSim-10 will be pre-populated, and what you'll see is this panel here. If you want to look at the geometries, there's a few ways, different ways you can do it. I like to look at just the poly data. So there's my half sphere. And then there's my the conductor, and then there's a dielectric embedded within that conductor. You can see that here in this view. Let me show you this. Right now, the nitrogen gas was present. That's why you couldn't see all the shapes. But if you deselect N2, then you can see all the shapes. You can get rid of the axes right there. There's my free electron that I've included. And if you click right there, you can see the dielectric, which I have modeled as absorbium. But I have included the dielectric constant within that material so that we can get the electric field calculation in there correct. Okay, so now if I want to look at particles, I expand particle data. And then I go to where we can see the first electron that I include. And that's right there. It might be a little small, so you can make it bigger. You can scroll in. There's my free electron that I initialize the simulation with. And then secondary electrons. So now I will scroll the time bar to the right, and bam, a new electron just formed. And like I just said, that formed at time step, well, that formed at time step 50, because I ran this for 500 time steps, and I dumped every 25. And this was my time step here, about 10 to the minus 13 seconds. Okay. And then, by the way, I made it so that the secondary electrons can hit another neutral to form another secondary population. That's how I get that cascading effect. And you can see this nice evolution of the electrons. And if you want to see what happens when they hit the dielectric, there's this population called heavy electrons, and those are the ones that stick to the dielectric once they hit it. Now, it's a little hard to see them because there's so many secondaries. So we turn that off. And for some reason, we'll give the simulation a minute to catch up. For some reason, the heavy electrons aren't showing up right now. And they have shown up in the past. Okay, so the heavy nitrogens are showing up, which means that the heavy electrons should be there. So there's nitrogen atoms or ions that also stick. And basically, that forms a quasi-neutral charge density on the dielectric itself. Let me. Oh, I know why. It's heavy secondary electrons. Okay, so there they are, immersing this dielectric. And like I said, the charge density is probably most likely charge neutral. I haven't, or close to it, I haven't checked that, but that would be a time dependent thing also. Okay. Now, the cool thing about this is that you can actually visualize the fields and the particles in the same plot. And so what I did was in this plot here, so if you go back to, if you go back to VSim, and now let me remove the particles. And then now let's plot magnitude of the electric field. And then in order to look in the middle, we need to clip that plot. And now we can see the field. And if you want, so you can superimpose the particles on top of that. Now, and there they are. They kind of clash with the color table that's already there. So you can actually, I'm not going to get into this right now, but one of the powerful tools of VSim is you can open up a visit plot. And if you're not, a visit window, and if you're not familiar with visit, feel free to send me an email and I can help you out with that. For some reason, so that's how I got these particles as black and white here, was I opened up a visit window. And if you right click here, then you can do open GUI, and then that'll allow you to open up this visit window. And you can you have a lot more options in visualizing the data if you do that. So if you want to know how to do that, then I can help you out with that. It's a pretty powerful way to visualize data in VSim. Okay. So now let's look at some results. And let's take a look at the effect the plasma formation has on the electric field. So at the early time, this is what the electric field looks like. The color scale goes from 0 to 10 million volts per meter. So this is a very, very large electric field, but that's really just because the distance is so small. You know, the distance from here to here is about 175 micrometers. And the potential difference was close to 1,000 volts. And then at later times, you can see an effect. By the way, this is the same color scale here. But it's a little hard to see what that effect is. And so what I did was I took this line out along here, and I plotted the data on the same axes, or on the same plot. The black curve is the potential at the late time. The yellow curve is the potential, or the electric field. It's the magnitude of the electric field at the early and late times. And you can see this effect right here that the plasma is having on the electric field. And you simply do not see this unless you use floating boundary conditions, which allow the plasma potential to dominate or to affect the potential difference. And then down here, you can see the impact on the electric field within the dielectric itself. You can see that the electric field has increased within the dielectric. And so this is the region where the dielectric exists. I took another cut. So if we go back, I took a cut along the top here. And you can see also this impact on the dielectric. Early time is black, and then late time is blue in this plot. And so you can see that within the dielectric itself, the electric field has increased. Next, I was curious how the shape of the dielectric impacts the electric field. And namely, basically, I wanted to know if I'd get at least qualitatively the right answer. I think everyone knows that if it's easier to get shocked with your finger than with the palm of your hand. So if you in Boulder, it's really dry. And I got shocked so much that I learned getting in and out of cars that I learned to use the palm of my hand. And so I said, well, qualitatively, we know that the charge density will be bigger near a pointy object. So does VSim capture that physics? So I did the same simulation, but I replaced the disk with this cone. And again, I modeled this as a dielectric, same dielectric constant. And I included those accumulated electrons on the boundary or on the surface. So then now let's go ahead and compare. So this is the data from the simulation with the cone here. And this is the disk-shaped dielectric. I picked the maximum, from each simulation, I picked the maximum in the electric field, and I'm plotting that. So they're not at the same time because the field evolves differently, but I wanted to compare with the max. I wanted to compare the max from both simulations. So the color scale here goes from 0 to 1.2 times 10 to the 7th volts per meter. And we can clearly see that the pointy object has a very large electric field, right where we would expect. And so qualitatively, we're capturing, this is a good sanity check to make sure that we are getting that correct. And again, I took a cut through or a line out from both simulations along this line. And this is from the cone here, and then the blue is from the disk. And we can see a large peak in the magnitude of the electric field right here where the red is. Now this, of course, will impact the electric field within the dielectric. So you can see the dielectric extends a greater distance along this path here compared with the disk. And so this whole region here is where the cone is, whereas only this little short region is where the disk is. But the electric field is much larger in the cone, or it's larger in the cone compared with the disk. So I took a line out along the top part of the dielectric to get a slightly better comparison. And again, you can see that within the dielectric, the electric field is larger. So I guess one conclusion would be, just kind of that the simulation seems to be behaving correctly, at least qualitatively, and open things with the palm of your hand, which was the disk was supposed to represent the palm of your hand, and the cone was supposed to represent the finger. So VSim can be used to model corona discharge involving complex dielectrics with varied shapes. And by complex, I mean varied types of dielectrics with varied shapes. So we can apply constant and time-dependent potentials easily in VSim. So for example, if we went back here, this potential here, which I set to 0 volts, could have been a time-dependent potential. Could have been some RF source, for example. VSim includes many collisional processes. So you can put in ionization, elastic, charge exchange, excitation to realistically capture all the processes that could occur. And then we, of course, can include secondary electrons off of surfaces. So for example, once the ions hit this cathode, you're going to get another source of electrons that can be supplied, and we can model that. these simulations just simply didn't run long enough, and I'll get to that in just one more second. In VSim, new to VSim-11, you'll be able to import your CAD and assign a dielectric to that shape. So these shapes were made within VSim, and then I was able to use space-time functions to assign the dielectrics correctly. But soon we won't have to do that. Now, just for clarification, this has been possible with the electromagnetic field solve for a long time. So this new capability will be with the electrostatic field solve. We can model the electric field in your dielectrics. And what I'll be doing soon will be testing out speed limited pick to see if we can speed up these computations and include those ion effects, which become very difficult to do as you get closer to an atmosphere. You know, at 1 torr or 1,000th of an atmosphere, the mean free paths aren't so small. But when you, for denser material or denser neutrals, these are very small grids. So the time steps are very small currently. Okay, so that is the conclusion and the end. So any questions?
If you'd like to ask Daniel a question, you can type it into the Q&A box, or you can raise your hand and we can give you, if you would like to ask it that way as well. And I'd like to say, Daniel, this has been really cool to see this all come together. Daniel Main is one of our application engineers, and I've said this in some previous talks, but one of the things that I really think makes our company that I'm really proud of is our application engineers. As you can see, they are wicked smart, every single one of them, and they work incredibly hard to help you figure out how to set up a problem. This came to us from a client who had it, and at the first time Daniel looked at it, he didn't know right away, like any problem that we approach in science, right? And you think on it for a minute and you come up and you test it out like he showed, right? You do those sanity checks, as you called them. And it's actually been really exciting to see it all come together. And I can actually see from our attendee list that there's several of you that have worked with Daniel. So you probably know exactly what I'm talking about and how he's been able to assist you as well. So from that, I'll stop talking for a minute. And you've got, from someone who's worked with you previously, Daniel, you've got a question.
So Daniel Esposito asked, what's a large pressure? I consider anything approaching an atmosphere a large pressure. And that's just my opinion. And then with SLPIC, do you think an atmosphere will be tractable? Yes, Dan Fairclough, hello, by the way. And yeah, I think I'll be able, I'm hoping anyway, to really speed up these calculations. I'm going to be working on that as soon as this workshop is over. I'll be working with the folks who developed it, SLPIC, and try to use that method in my corona discharge modeling.